program for us that you'll find in the labs directory, and it is called arbwrite.c. And basically what arbwrite does is you pass it 2 command line arguments, so you invoke it like arbwrite AAA BBBB, and it takes these 2 command line arguments. Actually, I take that back. It actually takes 3. And it tries to set the pointer of the first command line argument, and interprets this as a pointer, that like process address space, some type of pointer, and it tries to set that pointer value equal to the second command line argument. So in this case, it tries to set OX414141 equal to OX424242, since 424242 is B. And then eventually these C's will just be your shellcode, just putting your shellcode on the third command line argument. And luckily in this case, I tell you what the address is of where your third command line argument is. So we don't have to go digging through the debugger for where your shellcode is located in memory. And you can see basically I'm interpreting those first 2 command line arguments as pointers, pointer 1 and pointer 2. And I'm trying to set pointer 1 AAA equal to pointer 2 BBBB. So what we could do is set, if we made AAA like a return address, the return address for the main function, and set it equal to the address of our shellcode, then obviously our shellcode would execute. But there's a lot of other things you can change in memory besides the return address to gain control of EIP. As you can probably imagine, if you can change any 4 bytes of memory in a process, there's like a lot of different ways you can gain control of EIP. There's lots of function pointers floating around, and you can overwrite those, and other sort of important things that are eventually used to control the EIP. And we're going to talk about some of those to overwrite some of them. And I'm going over this because in exploitation, you often get into a scenario where you can arbitrarily change 4 bytes of memory. It's a pretty common scenario. You're corrupting something like a C++ virtual table, and it allows you to basically just like change 4 bytes of memory or something like that. So, just to give you an example, you'll want to compile arbwrite with GCC, so like so. Oops. Yeah. You won't have that issue. And you can see I get all of these warnings, basically a warning for each line of my code because I'm doing like the nastiest C programming ever to implement this. You know, programming an application that is supposed to override its own memory at will obviously will cause some issues. Or at least the compiler is going to say, I hope you know what you're doing. And if we just run it like AABB, like that, we'll get a crash. Unsurprising because it's trying to set, you know, basically if you know C, it's trying to do this operation. And since 414141 is an invalid address, we get a segmentation fault. So does everyone understand what arbwrite is doing basically, with what its purpose is and how it works? And we're going to leverage this or use this to experiment some with overwriting random ranges of memory and see what we can overwrite to gain control of the IP and cause our shellcode to execute. Okay. So the first thing we're going to look at overwriting. So the first thing we're going, like our first target for overwriting, we already know about overwriting the return address, and honestly, if you can overwrite anything you want, the return address isn't the best option because sometimes they're kind of hard to locate. But there's other more static things that are even more reliable than the return address. And the first thing we're going to talk about is the global offset table. And if you know anything about Windows, somewhat like the import address table, basically it's a table of function pointers in the process address space that the table just points to where imported functions are located. So when you compile a program like Hello World that just says printf Hello World, at compile time, the compiler has no idea where the printf function is actually going to be located. Okay, printf is the libc, or like a DLL in Windows, the shared library that contains the printf function is loaded at runtime. Is everyone familiar with this sort of like process loading type of functionality? So, you know, otherwise, if you did do that, every time you write hello world, it would have to statically link the entire libc to your simple hello world program, and you would get this huge, like, multiple megabytes size library attached to your 4-line piece of C code. So it's not efficient to just add in the printf code to everything. So instead, the compiler says, okay, I have no idea where printf is going to be. So instead, at runtime, I'm just going to use this global offset table to discover its actual location. And when the process actually loads, the operating system is going to come in, attach the printf code via a shared library to the process. It's kind of like loading a DLL in Windows. And then the operating system loader is also going to come into this global offset table and fix up the global offset table to say, okay, printf is actually located at OX B7 FD whatever. So if you were to look at like a C program, and you had something like a call to printf, like printf stuff. If you look at the underlying assembly in the debugger, you would actually see something like, and I'm simplifying a little bit, call, say like got 0. So like call the 0th entry of the global offset table. Or if you had something like, you know, str copy, blah, 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 you'll see call got 1. Because, you know, printf is the 0th entry of the global offset table, and str copy is the first entry of the global offset table. And that way, we do not have to have the actual string copy or printf code in our simple application. These are just in the shared library that gets loaded at runtime. And if you were to look at the global offset table and at compile time, you would see that these entries are basically 0 equals OX 0 0 0 equals OX 0 0 0. But then when you actually invoke the program ./program, the operating system does a lot of stuff, and one of these things is, okay, I see that you rely on the standard libc library that provides string copy and printf, so I'm going to load that into your address space. Automatically just going to force that into your address space, and then I'm going to come to your global offset table and say, okay, I put libc at OX B7 1000 or something like that, and since I know you're using string copy and printf, I'm going to come to your global offset table and set this actually equal to where these are located in your process address space. How does everyone feel about that? Does that kind of make sense? So in Windows, these are, we're talking about like DLLs, like user32.dll and so forth, that get automatically added to your process address space when your program runs. And with Linux, we're talking about things like the standard libc library. So if you didn't do this, you would have to statically link the application, and you would have to you know, have the actual printf code in your binary, and then your simple hello world binary would be like multiple megabytes big instead of it being like 4 kilobytes. Because everyone just shares that same pool of code instead of having to have that same pool of code attached to every binary. You should always think about the design decisions for why people do things these ways, just helps you remember them. So instead, we're actually calling through, indirectly calling through this global offset table. So what we're going to do is we're going to tell Arbright to overwrite its global offset table. So we're going to overwrite the global offset table associated with printf, global offset table 0 or something like that. And instead of it pointing to a legitimate libc address, OXP7EF, blah, 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 we're going to make it point to our shell code, OXBFF, something, something, something. So once we perform this arbitrary overwrite, when would our shell code actually get executed?
Whenever we call printf.
The next time we call printf. Next time we call printf, it's going to try to call for that global offset table again, and then bam, it's going to execute our shell code instead. So let's do that. So we can actually look at the global offset table and its contents using the objdump command again. So if you fire up your virtual machine and do objdump -R, I don't know if you guys write down, we'll be using that a few times, then the program name Arbright is basically telling you the contents of the global offset table, or not actually, I shouldn't say the contents of the global offset table, or where the global offset table is actually located. So in this case, it's saying the global offset table entry for printf is located at 804967C. The global offset table for puts is located at 8044680, and the global offset table entry for exit is at blah 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 684. And you can see these are like contiguous in memory as well, 7C, 8084, and so on. Notice so that it doesn't know what the actual contents of these entries are. That's because they're all basically 0 at this point, because the operating system hasn't come in and filled out those values. It's just looking at the binary on disk. Okay, so here's a question for you guys. If we can arbitrarily change 4 bytes of memory, why not just change the next instruction to be a jump to our shellcode or something like that? Why wouldn't that work? Yeah?
Because 4 bytes isn't enough to jump to those sections, right?
It could be, if you do a short jump. You can't do it because the text segment where your code is read only. If you tried to change your own code, it would cause a segmentation fault because your code is marked as read only. You can't do this crazy polymorphic stuff as your code is running, unless you do some pretty gnarly stuff. So it has to be memory we can change that will allow us to gain control of EIP, but it also has to be writable. Okay, we also actually have to be able to write to it. The global offset table, by design, has to be writable because the operating system has to come in and fix up these values for us. It's expected that they're going to change. So when we're looking for these targets, when we have like an arbitrary 4-byte overwrite, it has to be writable, and it has to eventually lead to control of EIP. Okay, so if we look at the global offset table and the corresponding source code for the application, we can see that there's an exit, because we're actually calling exit, so it creates an entry for it. And there's a printf, because we're calling printf, but there's a couple other kind of confusing things. There's puts and this libc start main. So to clarify, whenever you call printf and you don't pass it any additional arguments, like the modulo x, you're passing these additional arguments, it actually performs an optimization. So like in this case, we're only printfing a string. There's no additional arguments. We're only printfing the string pop-a-leg-bot, here my call. And whenever you do something like that, it actually performs an optimization. It just calls puts instead of printf. The compiler is doing that, just because it's a little bit faster. And these other functions you see, like libc start main and so forth, these are implicitly called by your program and you just don't see them in the source code, the compiler is basically just putting them in there because main actually is not the first thing to be called in your program, just part of the way the Linux operating system is working. So those are just a couple things to keep in mind. But obviously you see that you're using printf and exit, so those appear in the global offset table. So what we're going to try to do is overwrite one of these global offset table entries with the address of our shellcode and then get our shellcode to execute. So first off, you need to get a copy of your shellcode in this directory. So you have it close by to use. So I have mine right here. Already. Okay, so that's my shellcode, exec to E, then sh.
Corey, if we change the GOT table, doesn't that mean that any other function that we have running will also suffer?
No, because you're only changing the global offset table for the that particular function. It only affects the one function.
So every process creates its own GOT table?
Yes, every process, every executable has its own global offset table.
And what, do they just copy a main one somewhere? Because I assume that the copy of libc stuff is the same for everybody, right?
Yes, but they can't do like a common copy for everyone because libc can potentially be loaded at different addresses for each process.
Isn't that a functional Linux, though? No?
Are you asking, is it a function of Linux to load things at different addresses or to have everything, to have like
to have a common global offset table? I mean, because I guess wouldn't it assume that every process might need something, and so it would have it loaded up ahead of time, or I guess not?
Basically, just by design, it has to do it on a per process basis because every process is going to be different. And each process might have libc located at a different address. So like hello world might have libc loaded at OXB7 1000. And my basic Vuln application might have libc located at OXB7 2000 and so on. You just can't make any assumptions about where libc is going to be loaded in your process address space. So, and it's loaded for each process. So it can be different for each process, so you have to do the global offset table on
But as a coder, I don't have to do that. I just assume Linux is going to load that for me, right, I guess?
Yeah, you just assume that it's going to load it for you. That's correct. But you have no idea as a programmer where it's going to be loaded. You're relying on the operating system and its process loader to go in and fix up all those global offset table values for your process at runtime. Does that clear things up at all, or is there more things that
I think I get it now.
I know it's a little bit confusing. It's just, yeah, it's hard for me to explain it without relating it to like Windows and how they do it the exact same way with the import address table and DLLs, but then I'm not really explaining the issue. I'm just relating it to something. So I know it's confusing. But just know that the global offset table is a per process thing. Each process has its own unique global offset table. Okay, so everyone has a copy of their shellcode in the labs directory. And we're going to use argwrite to execute some shell code. So let's overwrite the global offset table for printf. All right. So my first argument is what I want to overwrite. So I'm going to put in the address for the printf global offset table. Remember, I have to do this backwards because we're in Little Indian world. So you can see I'm just, first argument is the address of what we want to overwrite, 0804967C. Remember also that I'm not doing some kind of system-wide change or system-wide back. I'm forcing ArbWrite. ArbWrite is programmed to, change itself in this really contrived way, just for, example's sake. And so we're forcing ArbWrite to change its printf global offset table when it's loaded this time, based on the arguments we're passing in. And what do we want to set? What should the second command line argument be? What do we want to set printf equal to? Yeah?
Starting location for the shellcode.
Right, and which is what right now? We don't know. So for now, I'm just going to put in some placeholder values, B, 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 B. And we'll go and figure out where our shellcode is in a second. And then the third command line argument is just going to be our shellcode. We're just going to dump our shellcode in the command line. That way we have it in the process address space somewhere. Because it turns out that anything we put on the command line actually ends up in the process address space, even if it's not copied into a buffer or something. So there we go. First command line argument is the address of printf. Second argument is the placeholder value. I put 4B since the address is 4 bytes long, just like the placeholder value for now. Using these placeholder values is important because if the size of your command line arguments change, things will move around in memory a little bit, okay? And that's also why I went ahead and put the shellcode on the command line. As a third argument, cat bin.sh.shellcode. You can use your hello world shellcode or your own custom developed shellcode. In fact, I encourage you to do that. And notice this tells us that the third command line argument is located at OXBF-FF-F770. The third command line argument is our shellcode. Because first command line argument, second command line argument, third command line argument. I basically just programmed ArbWrite to tell us the address of the third command line argument to make our lives easier, so it automatically just tells us where the shellcode is located. So, if we change these 4 bytes of B's to an actual 32-bit address of our shellcode, OXBF-FF-F770, we'll see what happens. Okay, so I overwrote the global offset table associated with printf. I overwrote it with the address of my shellcode so that the next time printf should be called, it should execute my shellcode, but my shellcode was not actually executed. If we look at the ArbWrite source code, we can see that the actual arbitrary overwrite occurs right here. Pointer 1 equals pointer 2. And the reason the shellcode was not executed was because this actually is not a printf call, this is a puts call. Because of that optimization I told you about. So we overwrote the printf global offset table, but printf was never called again. So our shellcode was never executed. So what I want you guys to do is try some of those other global offset table entries that you find with the obj-r command and see which ones actually execute your shellcode. So try, for instance, the puts global offset table, the exit global offset table, and you can even try some of those libc ones if you want. Okay, so for those of you that have worked through this, did anyone try gmon start? Not real confidence inspiring. Did anyone try either of these like libc things, like start main? Yeah, it probably wouldn't work. So printf, did that work? Shellcode? Yep. Puts, did that work? Exit? Okay. Yep. So the global offset table is one entity that is commonly leveraged. That's commonly leveraged when you like have an arbitrary 4-byte override to get your shellcode to execute. Butch, did you get the your shellcode to execute on any of those? Okay, which entry were you trying? Were you trying the puts one? 08049680. That one should definitely work. And so to use that one, you would do something like don't know what my address is yet. I'm just putting a placeholder value in. And I'm replacing that placeholder value with the address of RB3 BFFF770. We're doing it backwards. It's a little Indian. There you go. That should work. Okay, so we're going to talk about another target we can use that's used in Linux, and it's the destructor table, which is basically just a table of function pointers that are called whenever a process is being torn down by the operating system. So Linux, or GCC in particular, has this handy feature where you can register a list of function pointers to be called whenever your program exits, if you need to like clean up some memory or do some logging or something like that. And whenever the program is getting torn down and exiting, the operating system will just automatically go through and call all those functions that are on that list. So if we put our shellcode on that list, our shellcode will get called when the program is exiting. Okay, and so you can investigate the destructor by using this command, objdump again, objdump-s-j.detours, which is what that list of function pointers is called, and then the binary name rbright. And you can see what this means. Usually no one uses this kind of like obscure, weird feature. No one actually uses this in practice. It just exists for whatever reason. And right now it's telling us the list is empty. FFFFF signifies this is the start of the list. And then the first entry is just 0, so no entries. So I want you guys to try to overwrite the destructor with the address of your shellcode and get it to execute. And it's not going to work right away. And I want you guys to play with it a little bit and reason about the values here. So if you just overwrite the F's, it won't work. Because the F's are there to signify the beginning of the list. So if they're not all F's, then the operating system won't try to process the list. So instead, you'll have to try to overwrite like the 0s would be instead of the F's. And so the 0s would be at this address plus some offset.
Sorry, can you explain that again? So the detours is just something that's tagged on at the end of any GCC?
Yeah.
But and those 3 addresses are instruction?
So these aren't addresses. This is saying the destructor is located, the destructor list is located at this address, 8049590. This is the contents.
Okay.
The first entry is FFFFFFF, and that just means this is the start of the list, just like sanity checking values. And then the first entry in the list is 0000, which means the end of the list. So right now, the list is empty. And in fact, if you do this command on most Linux binaries, you'll see this is empty because no one really uses this feature, except hackers and virus developers. So what will happen is if you try to overwrite 8049590, it won't work, because then you'll be overriding these sanity checking values, that, and the operating system won't try to process the list. So instead, you have to overwrite 000, these zeros, which is at 804959 plus 4. Right, so you need to overwrite 8049594, because that's where the zeros are at. The F's are at 90, zeros are at 94. That makes sense? Yeah. Has anyone got their shellcode executing with the destructor yet? For those of you that have already gotten those, I'm going to let people work on this for like 5 more minutes. I challenge you to try to overwrite the return address with arborite, the return address of name with arborite with the address of your shellcode. To try to get it to work that way. So here's something to be aware of when you have like an arbitrary 4-byte override situation. Let's say this is the program that we're exploiting. Our arbitrary 4-byte override happens up here, pointer 1 plus pointer 2. We're assuming that we've corrupted some I'll control these values. And this is some real application. And then, there's some logic in here. Then 100 lines later, we have an fprintf statement. 100 lines, more code, string copy. 1,000 lines, more code, exit 0. Which global offset table should I choose if I want to write the most reliable exploit possible? Exit. You would want to overwrite the fprintf global offset table. The reason is the program would have to survive long enough without crashing to reach this fprintf statement. If you have performed a buffer overflow and have corrupted a whole bunch of crap on the stack or the heap, it's possible that when you're accessing one of those values, you will cause a crash. You corrupted some local pointer that can be used for exploitation, but it's still dereferenced, and it causes a crash. So you need to get your shellcode executing as soon as possible because you have put the program in an unstable state. So you want to make that shellcode happen as quickly as possible after you've performed, the overwrite. So chances are there's 1,000 lines of code, and you've corrupted a whole bunch of local variables. There's no way you're going to get to the end of the function without crashing before your, before your shellcode starts to execute. So that's just something to keep in mind when we're trying to develop reliable exploits. You have to sometimes survive long enough to get to the return address or something like that to get to the return. And if you corrupted a whole bunch of local variables, you might have caused the program to become unstable and crash. And if it just crashes, you'll never get to your shellcode execution. Do you guys get the destructors executing your shellcode? Okay. Anyone get the return address executing your shellcode?
Question. So the return address is always right above the EBP?
Yes.
Is it always contiguous?
Yes.
So if you just subtracted 32 from the EBP, if you knew the EBP and you subtracted...
it should be EBP plus 4.
Okay.
Because at EBP, pointing to EBP is the hold stage frame pointer. And then right above that, so 4 bytes later, since that's a 32-bit value, is the return address. And that's just the architecture standard. That's the way the Intel architecture is working in x86 mode. Occasionally, you will see like frameless functions that don't use EBP. I see that in x64 a lot, where EBP is not used at all. And that is sometimes just done as crazy compiler optimization when it uses heuristics to deem that that is more efficient than actually setting up a stack frame. But you don't really see that in x86, only when you're talking about x64 mode. Okay. Remote guys like Butch and Debbie, did you guys get your shellcode executing with the ArbWrite program? With the destructor in the ArbWrite program? Okay, so let me walk through that one as well. So first of all, we want to figure out what address we're trying to overwrite. So like I told you guys, this is the address of the destructor, but we actually want to overwrite the zeros, not the f's, since those f's have to be there as like a sanity check from the operating system. So instead of, we want to overwrite 8049594. Since this is 4 bytes long, 4 more bytes will get us into those zeros. So the first address is the address what we want to change, which is that destructor's address. Placeholder values. My shellcode. And I see that my shellcode is located at OXBF-FF-F770. So we overwrite the destructor, and then when the exit call happens and the process is being torn down, the operating system sees that there's this address in the destructor's list, and it says, okay, the program must have registered the destructor to be called to clean up some memory, or do some logging or something like that, so I'm going to call that. But lo and behold, it is actually our shellcode, and our shellcode gets executed at the end of the program's execution. So, like I was just explaining, where you have to make the program survive long enough to execute your shellcode, when choosing what you want to overwrite. Sometimes the destructor is hard to use because it only gets called when the program is exiting, and that might be, far away in proximity to the place in code where the program exits compared to the place where you corrupted everything. So this would really only be a good option is if you could perform your corruption and then cause the program to exit soon afterwards. Otherwise, we'll probably end up crashing the application before you get to the normal termination of the program. If you just call the segmentation full, the destructor list will not be full. How's everyone feel about that? Okay? Is everyone ready to hack Corey's crappy allocator? Charles, did you figure out how you would cause that arbitrary 4-byte overwrite?
I think so.
Okay, I want to try explaining.
So it gets to the point where it sets the previous pointer, the next pointer, the next to the previous.
Yeah, the unlink operation that I was drawing up there.
And if you set one of the pointers to the value that you want to change and the other pointer to the value that you want it to have, then it'll assign that value to what you provided.
Yes. So, like Charles was just describing, we get to a point when we're going to unlink that chunk from the free list, and we're removing it from the free list, and we do something like this. Next pointer, previous pointer equals previous pointer, and then next pointer, previous pointer, next pointer equals next pointer. So we control, at this point, next pointer and previous pointer, because we have overflowed and corrupted those values. In your examples, you probably overwrote them with AAAAA, 414141. So what the program essentially tried to do was set it's gonna like a lifespan of like an hour or something. There we go. Sure. It's trying to set 41414141 equal to 41414141. 41 is 414141 is a bogus address, so that causes your crash. But you know that you control next pointer and previous pointer. So let's forget about this for now. Before we venture into this, I'll say it's probably the hardest lab in the class, so prepare yourselves. There'll be lots of twists and turns. The excitement that is Corey's crappy allocator. But we know that we control next pointer and previous pointer because of our heap corruption. Everyone with me on that? This line of code gets executed in the unlinked chunk function, which says next pointer equals to previous pointer. We control both those pointers, so we have an arbitrary 4-byte memory overwrite because we control the destination of the overwrite and the value that it's being overwritten with. If we set next pointer equal to the global offset table, and this equal to our shell code, then we will set the global offset table equal to our shell code, and then eventually our shell code will execute. There's a couple nuances here though. First off, we're not just setting next pointer equal to previous pointer, okay? We're setting next pointer arrow previous pointer equals previous pointer. Who in here is a wizardly C programmer and can tell me the implications of this operator?
It's accessing a field in a structure after dereferencing.
Yes. So, if the address of next pointer was 1000, what would the end result of the address be after this operator is applied?
Depends what that structure is.
Yes.
What it is in the
So,
structure, what size it is.
Good job, yeah, good job. Most classes struggle with that concept. So let's go back and look at the contents of that control block structure that pointer is referenced. Okay. So this is something you're going to want to keep on a piece of paper since we'll be accessing or using this field. You want to know exactly how it is laid out. So this structure looks like a control block. We have int avail. We have int size. We have a pointer, so I'm just going to say void to make it left to right. Void next. I'm just simplifying here. The names are exactly the same. Void previous. Make that more clear. Next free. Previous free. Okay. So this is our control block structure. Let's assume we have a control block pointer. So I'm just going to say CB control block pointer, and let's say our pointer is pointing at a control block located at address OX1000. 1000. This is just the address and memory of where the control block is located. So that's what pointer is equal to right now, right? Because he's pointing at locations in memory. So right now, control block is located at OX 1000. So that is what our pointer is equal to. If we do CB avail, what address am I talking about? If I say CB next free, what address is that?
1008.
And then previous free? Nope. Trick question. Yeah, C. So 1000 C. Okay, good. So you guys understand that concept. So when we do something like next pointer equals, or next pointer previous pointer equals previous. In the time that our corruption happens, let's say we have overridden next pointer with 41414141. We are basically doing 41414141 plus C. No, plus. Yeah, plus C, that's right. Plus C, OX, C equals OX 41414141. So, what address do we need to corrupt the next pointer field with? It's the global offset table minus OXC. Okay, so we want to override next pointer with global offset table minus OXC. That way, when this plus C gets tacked on, the net result is 0. And we're basically saying global offset table equals address of our shellcode or whatever. People look mystified there. How's everyone doing today? That kind of makes sense? I know if you're not familiar with like C structures, this will come across as a little bit weird, but you just have to remember that this operator is basically just adding some offset onto this pointer, and you control that pointer. So in this case, it's adding an offset of OXC because it's the plus 0, plus 4, plus 8, plus C member of that structure, and then setting it equal to another value that you control. So your challenge is to take your crash from the memory heap allocator and turn it into something that executes your shellcode. So this will be pretty hard, and there will be some struggles along the way and some things I haven't quite told you about yet, but I want you to try to discover them on your own. But I think you guys have a pretty good grasp of this material, so hopefully you'll do well. So yeah, I'll let you choose your own target, what you pick in the global offset table, or you could pick the destructor, or try to pick a return address or something like that. It's totally up to you. And you want to try to override it with the address of your shellcode. What I will say is that if in your crash you were using small allocation sizes, like just 10 bytes or something like that for the chunks you were creating, I suggest you adjust those to be bigger, like 128 bytes, so that they are big enough to hold your shellcode. Because it'll be easier for you if you put your shellcode on the heap, so you want your heap chunks to be big enough to store that shellcode. So if you make them like 128 bytes each, that's probably best. Okay, so I'm going to let you guys start on this for I want you to just work on it 15 minutes without me giving you too much help, because I want you guys to see how much you guys can get figured out. Then after a while, I'll start feeding you more and more hints and working you through the process of exploiting it. And then right when you think you've got everything set up, you will discover that it still doesn't work. And I'm curious to see who can debug that fun little issue. So yeah, if you think you have everything figured out and it's crashing, no surprise there. I sort of expect that will happen. Some of you will get lucky and you won't get that crash. Another thing you want to think about is when you're corrupting your control block meta information, what do I want all of these values to be set to? All right, you're not just corrupting the next and the previous pointers. You're also corrupting the available and the size fields. So if you corrupt this and set the size equal to 0, then your exploit is going to fail because the heap allocator is going to say the size is too small, so I'm not even going to consider processing these next and previous pointers. Or it might consider processing, but it's certainly not going to unlink it from the list and then cause the arbitrary 4-byte overwrite. So you have to be intelligent with what you corrupt all the values with. It's also similar if you have something like a stack overflow. You often corrupt a lot more things than just the buffer you're overflowing. And the return address, you often smash all kinds of local variables on your warpath to the return address. And oftentimes you have to be clever with what you override those values with as well. That way you can keep the program executing and stable long enough to actually hit that return address and get your shellcode to execute.